Welcome back. Today's video we're going to talk about actually several things. We're going to go through the steps to get your first program onto the AVR chip. We'll cover the hardware setup, the bare minimum hardware setup on a breadboard. I'm assuming you've already downloaded the Atmel Studio, and we'll open that up and show you how to get a new project started and set that up. And we'll put in the software we needed for the first program that will blink an LED. And when you get into the lab, I'll give you that software. It'll be on Blackboard. No, it won't be on Blackboard. It'll be in Google Docs, or I'll post a link down below in the comments too to that particular software. Particularly since this is a public video, I'll put it somewhere where anybody can get to it and download that. Okay. So, those are the things we're going to cover. Cover some of the quirks in Atmel Studio, like I said we needed to cover. So, once you've watched this, you should be in good shape to hit the ground running and get that first program, and know that your computer's working, know that you're able to talk to the chip, got all those little startup issues out of the way, and then you can work on your first actual software that you're writing yourself. So this is our initial hardware environment here. For programming this chip. It's pretty simple. We have a breadboard, we have the ATmega1284P. Now when I put this in here, I should point out, I'm sure you absolutely cannot see it. But if we look at this chip carefully, there's a notch right here that indicates essentially the top of the chip. Just like you see here, there's the notch in the diagram of the pinout, so that tells us where pin 1 is, and there's also a little tiny dot right there. So we got our chip. We know which pins are which because we can orient it with those dots. Let me explain how these breadboards work. Basically, each of these rows of 5 holes. Let me move it so I'm actually in the camera here. Each of these rows of 5 holes are connected together from here to here. There are little spring clips underneath there, and we can insert components, or we can insert wires like I have here, or just stick wires in and make a connection. So here I've got these wires here coming in for my power. I've got one wire connected into this pin here, and I should be a little more explicit about these pins. These 5 are connected together. They're not connected obviously to the adjacent rows. They're not connected across the ditch, and they're not connected to these pins down the sides. As we go down the sides, we have 2 rows that are connected from end to end, and if you look closely at a lot of breadboards, they'll have a plus and a minus. Some will have them switched. There's different variations, but typically all of these along here will be connected from one end to the other. Sometimes there's a break in the middle. All of these will be connected together, and we can use these for power and ground. So here I have my ground wire coming in from a battery. So I have power coming in from battery, or ground. I've got power going over this voltage regulator chip. The power is connected, because this goes in this pin, it's connected to that pin of that voltage regulator. This middle pin is the ground for the voltage regulator. It's connected to one side of this filter capacitor, and this little jumper carries me over to the ground rail. And then the last pin on this regulator is 5 volts out, and it goes to this jumper, which puts me to there. Okay. And I also have on this board, I've got a resistor and a LED hooked up. We'll explain how that works in a minute. And I've got my adapter right here. So we have our adapter here, and I'll pop it off. Wiggle wheel. Okay. And what this has is there's a 6-pin connector here. Let me see if I can get it some way that you can kind of see these 6 pins here. Those are the pins that connect to our programmer with the Atmel AVR, I forgot, AVR ISP Mark II programmer on the end that connects to our actual chip. I have this 6-pin rectangular connector. I think you can see that, the 6 pins reflecting the light. The other end just has the USB to plug into the laptop. And I need to get from that rectangular connector, which has this pin out here, to the various pins from here to there on the chip. Okay, so this little board here takes the 6 connectors right here, and on the back I have a set of connectors, the 6 connectors that go into the breadboard, and I have another connector for power and ground that go into those rails, so it supplies power and ground both to that 6-pin connector on the other side and to the chip itself. So I just need to remember to put that back in the right place. And the way that's wired, here's the pinout of the plug for the programmer. You've got master in, slave out there. We've got, that goes to pin 6, nope, pin 7, I'm sorry, master in, slave out. Serial clock, SCK, goes to pin 8, serial clock. And you can see that these pins have different functions. They can be used as just plain digital I/O. We can use them for this serial peripheral interface that we're using to program it. They have some other functions as well. Reset is the reset line right here, pin 9. Ground is the power ground, which is pin 11. Master out, slave in is pin 6, MOSI. And voltage, pin 2, is the same as the VCC, and that's our regulated power supply. So this little jumper just makes the connections between this and this with an intermediate stop at the power rails in between. And I think that's all I need to cover right here in terms of the hardware layout. Yeah. Oh, resistors. I'll do that next. We'll talk about why there's a resistor and series here. I go from pin 1 on this chip, which is the one we're going to be used to blink this resistor in our first program, to this rail right here, and in the same rail is my LED, which is connected there, and then the LED goes to ground. So I'm going to supply 5 volts with the chip, and then this is connected to ground, and I'll have a voltage drop across this resistor here to keep the voltage and current across that LED in control. Okay? So that's that. Okay, so here's our setup for the LED. We have our pin here coming from the Atmel chip or from anywhere else, and it's supplying 5 volts. We have the LED here. We have a spec for our LED that says that the LED is rated at 2.6 volts, 28 milliamps, or 0.028 amps, and then we go to ground and we have this resistor here. So how do we figure out what size resistor do we need, or why do we need it? Well, what we want is across this LED, we want to see that 2.6 volts at 28 milliamps, okay? And we've got 5 volts there. That doesn't work, right? Now, I know a lot of you haven't had circuits yet, and you may not be familiar with everything I'm saying here. Don't panic, okay? This will be covered in class as part of your electrical stuff, and by the time you graduate, you can do this in your sleep. But I want to just give you real quick how we figure this so you understand for this first lab, or at least have a clue. Okay, so we have 5 volts there, we have ground there, which is 0 volts. Basically, these are in series, so all the voltage drops across each individual element in our circuit add up. Kirchhoff's voltage law. The voltage law says if you went around this loop, you get a sum of 0. So we have a plus 5. We're losing 2.6 here, so we need to lose something in here. Well, 5 minus 2.6 is simply 2.4 volts. So I need to have a 2.4 volt drop across that resistor to leave me with 2.6 here. Now they're in series, so I know the current through both items are the same, okay? current going, if we make this a node, current going in equals current going out, Kirchhoff's current law. So I know that I'm going to have 0.028 amps at, is what I want. So if I get 0.28 amps to flow, I get 2.4 voltage drop across there, and then I'll be left with the 2.6 volts at that same voltage, the same current right here. So how do I figure out what the resistance needs to be? Ohm's law, I equals E over R. Current is the voltage over the resistance. It's very simple. We know the voltage we want for this resistor. We know the current we want. We need to find the resistance. So R equals E over I, and that's equal to my 2.4 volts over 0.028 amps. And if I do the division, that gives me basically 85 ohms. Now we may not have an 85 ohm resistor, I'm pretty sure we don't, so we could use a standard size like 91 ohms or 100 ohms, and that gives us a little margin for error because we don't want to overdrive that. These resistors, depending on what kind you get, they may be 2%, they may be 10%, they may be a 20% tolerance. So you want a resistance that's a little bit, a nominal resistance that's a bit bigger than that 85 the math gives us. So if we make this, we'll say we'll just make it 100 ohms, that's a nice round number. We'll get close to that 28 milliamps and close to that 2.6 volts across the LED, and it will light up nicely, but we won't burn it out. Okay? So that's how we figure the current limiting resistor in one of these LED circuits. Okay? And I think that's everything we need to set up for the actual hardware setup. So now we'll go over to the computer, we'll fire up Atmel Studio and put in that first program, and then we'll see what happens. Who knows? It might even work.
We're on the computer now. I have the program we're going to use just sitting here in Notepad because it's convenient. Let me minimize that, and we'll open Atmel Studio. And it's going to ask us some questions. Oh, see this grid here, by the way, while we're waiting? See the A and the B? Oh, now it just got clobbered. Well, you can go back, rewind the video, and pause it. But it's kind of an interesting example of the difference between human vision and machine vision, because when a human looks at that picture, they see the A and the B as different colors when in fact they're the same. It's going to ask about Arduino. No, we don't need to do any of that. So what we're going to do is we're going to do a new project, okay? And I've got the microcontroller chip sitting on a breadboard, hooked up through the programmer, hooked up to a battery, and all that ahead of time. So it's going to be a GCC, for GNU CC, executable project. And we can give it a name here. We'll call that Blink LED. And it's going to come up with a solution name that defaults to the same sample. It'll give you a default default location for your software to go. That's where mine goes because I've been using that. And you can create a new directory for the solution. That's usually a good idea to keep all these different things separate. And it creates an AVR 8-bit type project over here you can see on the right. It's not an Arduino board. It's not an Atmel board. You don't need to worry about user boards. We're not going to do assembler or Atmel Studio solution, just straight up right up top. And OK. And now it needs to know what kind of chip do we have. A couple of ways we can do this. We can drag down until we find it. Being lazy, I will type ATmega1284P, and it gives me a short enough list. ATmega1284P. It tells me data memory, the boot memory, EEPROM memory, things like that. It gives me a list of supported tools. Now I will mention we're using the AVR ISP Mark I. If you bought something, say a programmer from Pololu or SparkFun or something like that, you'll probably be using it as an STK500, but they're supported for that chip. So we say, okay. So it knows what kind of chip we're going to use, which it will need to know to set up the proper libraries that contain the definitions of pins and things. And the default comes up with include the AVR-IO.H. AVR-IO.H contains a number of things, the definition of parameters such as port B, things like that, and associates it with the necessary memory locations. But I've got this software here, and by far the easiest way to start to borrow somebody else's software is just to open it up, do a copy, and then, oops, if I click over here, it put the debug thing on. I don't want to do that, so I just click on it again, turn it off. Put that in, and I can just replace everything. Paste. Okay? And let's go through this one line at a time. Pound define means we're defining the FCPU as 1 million. That's the frequency of the CPU processor. And if I go to implementation, you see it's in it's used in delay.h. Okay. This parameter FCPU is used in this utility down here, so we want to define it before we get to that utility. And it's used in a number of other library functions and things. So usually I put that right up front. The factory default is 1 megahertz on a raw chip coming straight from the factory. We can change the fuses to do a divide by 8, or turn off the divide by 8 and run it at 8 megahertz. We can put a crystal on there, and that'll have some specific value. Include AVR-IO.H. That is where things like DDRB, which we talked about in one of the earlier videos, is defined. So here it is defined DDRB. And there's the actual memory location for that register, and you can see that it has associated bits that go with that. Here's port B's definition, pin B. You can have the pin, which is the entire register, or pin B1, B2, B3, etc., are all the the individual pins inside that. So those are defined in this IOM1284P.H. And Atmel picked that particular one because we told it was a ATmega1284P chip. So it went to the right place and defined these things the right way. So we include that AVR-IO.H because it has all the definitions of all of the I/O things that we're going to need. There is a utility called delay. We're including that in here so we can use some delays. And then we have our main. The proper syntax is integer main, and then it's void because it returns nothing. It really isn't an integer, but that's the syntax that works. So just do it that way. The open and close brackets or braces for the main program. The program itself is pretty simple. I'm setting DDRB, the data direction register for port B. Here I'm just clobbering the entire register and setting it to binary 00001. I could just eliminate all the leading zeros, but when I deal with registers and ports and things like that, if I put all 8 bits there, then it seems less confusing to me. So we're setting pins 1 through 7, which is all of the zeros as inputs, and pin 0, you start counting at 0, and this is the least significant bit on the right, setting that to 1. So pin 0 is going to be an output. An alternate way to do it, like we discussed in the video on binary arithmetic, would be DDRB or equals 1 shifted over by pin B0. Okay, and if we went back here, right click, pin B0 is equal to 0 right there. And I guess to be absolutely correct, we should have said DDB0, and now fix that, because in theory, they could change the numbering of the ports and the direction of the numbering and things relative to the pins, so I haven't run into that. But let's just, to be more correct, DDR-B0, okay? Again, just for software completeness. Now here we have a loop while 1. Obviously, 1 is always 1. It never changes. So this is our infinite loop in our software. Once we turn this chip on, we just want to run it for forever, right? It just runs. Just like when you turn your computer on, or your laptop, or your desktop, or whatever, your notebook, once you turn it on, it's just on, and it just keeps running, and it's running some idle tasks where it's waiting for some kind of input. On these microcontrollers, you have this infinite loop that defines the code that just repeats over and over and over again. So what it will do inside these braces, it will set, and this really to be absolutely correct, it should be port. And you can see where it comes up with suggestions. Port B0. So we're saying that port B, the entire register, or exclusive OR equals 1 shifted over by port B0. So we're going to take that 1, shift it over, in this case, 0 points or positions, and we're going to do an exclusive OR with 1. And if you recall from our binary video, an exclusive OR essentially just changes the state from 0 to 1, 1 to 0, 0 to 1, 1 to 0. And so it'll just, every time this particular line executes, the state of that output port will change from 0, which is off, to 1, which is on. And then we'll have this underscore delay milliseconds, so we will delay 800 milliseconds. And this is where it needed that CPU speed, so it knows how many clock ticks to sit there and park. In a lot of application program, you don't necessarily want to use the delay, because while it's sitting there delaying, it's doing nothing, right? It's just idle, and it won't look at anything, it won't do anything. But for this case, it's simple and easy, and that's the end of it, okay? So that's our program, and I can save that. And that program should just turn that pin B0 on and off and on and off every 0.8 of a second. So, assuming that everything is plugged into your chip, what I like to do, especially if it's a new chip or if there's any problems or what's going on, I come up here to device programming. You can do Control-Shift-P, or you can click on this icon right there. And it comes up, and under Tool, I'll pull that down, your choices are Simulator, which we're not using, or highlighted there, AVR ISP Mark II, and then a big long number. That big long number is the serial number of the specific programmer you have attached at this very moment. Okay? This is one of the quirks. If you're programming it and then you go to, things happen in this lab, people borrow the programmer, then you borrow another programmer from somebody else, and you plug it in, and it's got a different serial number, it's not going to work, because it's trying to program to the programmer with the serial number you have here. And in that case, you'll usually see both programmers listed here, and you have to flip it over, read the serial number, see what it is. The device, ATmega1284P, we set when we started this project. Interface ISP, that's just your only option. We apply that, and it's going to come up with a number of things here. One of the things it comes up with is the ISP clock. If you read the note, the ISP clock frequency must be lower than 1/4 of the frequency the device is operating on. So if our CPU is running at a megahertz, the fastest we can run our ISP clock, which is, I forget what the I stands for, but I think it's serial programming, something serial programming, The fastest we could run that is 250 kilohertz, but if there's a little mismatch between the clock and our Atmel chip and the clock and the programmer and things like that, it's better to not push it. You know, we could slide it up to 250, but that might work, it might not. Sliding it down to 125, that's a very safe setting, and it also just takes a fraction of a second to program. If we slid it all the way down here to a couple kilohertz, that's certainly safe, but it will take especially as the programs get more complicated, it will take a very long time to program. Believe me, you don't want to sit there and wait for it. So running this up to about 125 is a good thing to do. And over here we have target voltage. If I click on read, it comes up 4.9 volts. That's a good thing. Should be close to 5 with our 5-volt regulator. If I read the device signature, this is kind of an acid test to tell me, am I hooked up? Is it hooked up correctly? It didn't complain. I got a device signature. That device signature matches the ATmega1284P because it didn't complain. So I'm somewhat comfortable that my physical connection between the laptop and the chip is okay, and the chip is at least alive. I will show you some other things here. This fuse page. Messing with fuses is a good way to brick the chip if you're not careful. It comes with this one checked right there, JTAG enable. I normally uncheck that one so that I can use the port C. Do not uncheck this SPI enable because if you uncheck that, then you can't program the chip anymore. The JTAG enable, it's another programming format or interface format. We're not going to get into most of these. There's this clock divide by 8. If I uncheck that, then we're turning off the clock divide by 8, and you'll run at 8 megahertz instead of 1. But for the initial program, don't mess with these, okay? All you can do is screw things up, so you know they're there, but don't mess with them. Just run with it the way it is, just to make sure you have everything working, okay? So I'm going to close that. That doesn't, and you can program through that interface, but it's less convenient. So I'm comfortable now that I have some kind of connection, but if I want to actually do some programming through some of these others, I'm using an ATmega1284P, you can see that, that says no tool. So the default tool that the Atmel Studio is going to use is no tool. We got to fix that. And this is where if you had switched tools, switched programmers, this is the tab to click. You know, either one of these will work. If you clicked on ATmega1284P, it gives up essentially the same window, just a different tab. You get the device window. If I click on tool here, select the debugger programmer, AVR ISP Mark II, and that comes up with the right serial number. If I was using somebody else, a different type of programmer, you know, we would pick that. And I believe it's here. No, whatever. If you get a programmer from Pololu or you know, off anywhere else, off of SparkFun or off of, you know, wherever you buy your stuff, read the directions for installing it. Now, ISP clock 125 kilohertz, that's fine. And you can see the little star right there, right there. It means this hasn't been saved. So until I save that, I can't really program save. A lot of times, all you have to do if you're having trouble programming is open this up, and you see that it's not saved, and you click on save, and then miracles happen. You know, the heavens open, and your software is blessed, and everything starts working. That's one of those quirks, okay? And you can see now also over here that it's changed to tell me that I'm using AVR ISP instead of none. That's right. So that's all working. I can close that now that I've saved it, but you have to click on save. The fact, until you click on save, that, either here or save everything, until you click that save, it didn't happen, okay? It just didn't happen, and it doesn't count. So our next step, is there any mistakes in my software? I'm going to make a mistake just because, not that I'm perfect and never make mistakes, but just for the sake of discussion, I go to build solution, and I will point out there are solutions over here on the right. You have solutions, you have projects, and then you have the individual files underneath those projects. I tend to use one solution for each thing that I'm doing. Other professors will put multiple projects up with the blink LED and something else and something else and something else under one solution, and that's their choice. I do it differently. You do it the way you want it. But again, when I did that build, it says I've got an expected semicolon before delay milliseconds. I got 0 warnings, 0 messages, 1 error. And it says it's on line 24, column 3. So it says I should have seen a semicolon before that point, and obviously that's what we did there. Sometimes when things are misbehaving and you have just a whole ton of library files over here on the right that you've included, right now we don't have much at all. Doing a clean solution will kind of give you a fresh start. That can be a good thing. So I'll do my build again, build solution. It'll take it just a moment, and it should come out clean. It'd be funny if it didn't, wouldn't it? Okay, so build succeeded. So that tells me that my software at least compiles. Does that mean it works? No, it doesn't mean it works. It tells me it at least compiles. We made it through spell check, essentially, right? The next step, to send it to the chip, click on debug, start without debugging. And the first time I do this step-by-step process, just to know. And what happened that you couldn't see, because all you see is my screen, is that there's a green light on the programmer that flashed orange for a second to tell me that it was in the programming mode, and presumably it sent the program to the chip, which is now blinking my light. And that's really the last bit of actually programming this. If I want to make sure everything is really working and it's just not software left over from last time, I can change that from 8 milliseconds to 800 milliseconds to 100 milliseconds. And as a shortcut, this little triangle up here, start without debugging, will run the whole compile and download process automatically without me having to sit there and click individual things. And there it flashed, and now I can see my LED is flashing about 8 times faster than it was. So I know that I changed the software on my chip, and that's all working, okay? Other quirks, I think that's other things. Sometimes when we're programming, if we're sharing pins, like when we put on the liquid crystal, some of the programming pins and the liquid crystal pins overlap. Sometimes that causes the programmer to sit there and flash red. The thing to do at that point is simply turn everything off, at least turn the controller board off, unplug the USB programmer for your computer, plug it back in, turn the controller board back on, then it'll usually work the second time. If it doesn't, remove the liquid crystal display. 90% of the time it'll program just fine with that liquid crystal display mounted. Every once in a while it won't. I'm sure there's a reason for it, but I don't know what that reason is. I'm just one of those things. There's ways to avoid it by not sharing those pins, but it's usually not a big problem. Okay, having done all this, now we know that we're talking to our chip. Our chip is working. We've got some confidence in our tool chain. You've seen how to do this. So your first programming assignment here in the lab, instead of just having one LED blinking, connect LEDs to pins B0 through B3, so you have 4 LEDs, and make those LEDs count in a binary pattern from 0 to 15, okay? So it'd be B0 would be on, then B1 would be on, then 0 and 1, then 2, then 2 and 0, and so forth, okay? So that's your first task in the lab here. It's very simple to do. I'm not going to tell you how to do it. I'm going to let you figure that one out, okay? But remember, we're writing to this port, and we have different ways to write to the port. We can just simply write, here I'm doing the exclusive OR equals to just flip one particular bit. I can just write things to that port. It's just a register. It's just a 8-bit byte that we can write whatever we want. I could write ASCII A in there, and it will interpret that ASCII A as a command to turn individual pins on based on that binary pattern. So those kind of hints should have absolutely given it away. If not, think about it. If not, you can always ask.
So here it is, all hooked up and blinking for us. Now I'm blinking at a fairly fast rate because I have this delay. I have this delay set to 100 milliseconds instead of 800, and I wanted to point out a couple things here. If I remove the power to the board, the light turns red over here on the AVR ISP Mark II. If I unplug the programmer from the USB port, it stops blinking, and because I've pulled that reset down, so if you've got it hooked up here, you need to be plugged in. Now if I unplug that, now we're back to normal operation. But just plugging this 6-pin connector in here, and when I plug it in, I match my red stripe to pin 1, which I marked with a dot on my adapter. Just plugging in like that kills everything. Restoring the power, we're all set. Now if I want to make sure that I've changed my software, I can come to that point, change that 1 into an 8. So it's a delay of 800 milliseconds. I can come up here and click on Start Without Debugging. And if you watch this light well, first it's going to go through the build process, but if you watch this light here, in a moment it'll flash orange. There it went orange for a second. We've reprogrammed it, and you can see that the blink rate has changed. That should be it. So we've got a program, we've written it to our chip, we've got the LED blinking, we know that we're writing properly because we can change it. We should be good to go, so stay tuned and enjoy the lab.